All right, what's up, everybody? Today it's another question, another day, another question. Um, Today it's 310 minimum height trees. This is going to be another topological sort problem, but this one is actually on Leetcode, so we're going to be doing that here. So yeah, let's go ahead and read the problem. A tree is an undirected graph in which any two vertices are connected by exactly one path. In other words, any connected graph without simple cycles is a tree. Given a tree of n nodes labeled from 0 to n minus 1 and an array of n minus 1 edges where edges sub I is equal to a sub I, b sub I, indicates that there is an undirected edge between the two nodes a sub I and b sub I in the tree. You can choose any node of the tree as the root. When you select the node x as the root, the result tree has height h. Among all possible rooted trees, those with minimum height are called minimum height trees. Return a list of all minimum height tree root labels. You can return the answer in any order. The height of a rooted tree is the number of edges on the longest downward path between the root and the leaf. So for example, we have the four edges. The connections are 1, 0, 1, 2, 1, 3. And you want to find the minimum height tree. In this case, it's 1. And then I guess example 2. What is this? 3, 0, 3, 1, 3, 2, 3, 4, 5, 4. So the minimum height tree would be 3 and 4 because the minimum height would be like, what is this? 3. Is this height of 3? Or is this technically height of 2? I forgot because sometimes you can count like the number of edges and then that would be the height, but I think let's just say the height is 3 because 1, 2, 3. And let's just say, for example, you were to choose 1, right? Then this would look like 1 and then 0, 3, 2, no, 1, 1 to 3, and then you'll have the 0, 2, 4, 5, and that would be a taller height, right? Because there's just an extra one. So that wouldn't be the right answer. So yeah, basically, let's get into the question. This is another topological sort question. So what we're going to be doing is what do you call it? We're going to be, let's see, we have an edge case here, which is if n is less than or equal to 2, then we just return I for I in range of n. Because n is the number of edges, I think. Wait. No, n is the number of vertices. N nodes. Yeah, so these are considered vertices, right? So if there's 2 of them, the tree would look something like this, or like in the opposite direction, 2, 1. I think actually it's from 0, so be 0, 1. I guess just replace the 2's. So it would look like that, right? And then with 1 node, it would just look like this, this. So we know with that edge case, we're just able to return a list of whatever numbers there are. Now we're going to initialize, what is it? We're going to initialize our top sort data structures in degrees and out degrees, right? And afterward, we're going to build the graphs, or like build the values within in degrees and out degrees. And then after we build the values, we're going to find our starting point, right? So our starting point here is going to be all vertices with what do you call it? With all vertices, well, all leaf nodes actually. So which basically just means all vertices with one 1 in degree, if that makes sense. And then while we haven't visited all nodes, while we haven't visited all nodes, basically we're going to erase leaf nodes and add the following leaf nodes. And then once we have visited all nodes, the nodes remaining in the queue are our roots for MHTs. Yeah, so basically we're going to create our top sort data structures. We're going to build the values within these our structures. And our starting point is all of the leaf nodes, because we're going to be basically doing sort of like a reverse topological sort. Because topological sort, typically we're going top down from what do you call it? From one point, and we're branching out, right? But then with this solution, we're sort of going back inward and upward to our root, and then the root is our solution. So yeah, it's sort of like a reverse topological sort, if that makes sense. And so this is our condition for basically going back inward to find our root nodes for our solution. So it might make more sense as I start typing it. In degrees is equal to this, out degrees is equal to this, and then we're going to build in degrees and out degrees for I in range of n. In degrees, I is equal to 0. In degrees, oh wait, whoops, out degrees, I is equal to set. So actually no, we can use a list. So basically what we're going to do here is this is just setting up the in degrees and out degrees, and we need one for every number, and then so, well, I mean, I guess that's normal. I don't know why I'm really explaining that. And then so for a, b in edges, because there's technically no like front or back, right? So I'm just calling it a and b. We're gonna do out degrees a dot append b, and we're gonna do out degrees b dot append a. The reason why we're doing both directions, and typically when we do top sort, we only do like from the first to the second. The reason why we need to do both now is because this is undirected. It's undirected, which means we can go from 0 to 1. So in this example, we have 1, 0, right? So in our normal topological sort problem, we'd go from 1 to 0. But since it's undirected, we can go from 0 to 1 as well. So we need to handle for both cases. Same thing here, in degrees, we have to plus equals 1. But also for in degrees of b, we also have to plus equals 1. Yeah, oops, forgot to state that we need to create our queue. So once again, let's go all the way back up from collections, import dq. So yeah, we're going to create a queue here, is equal to dq. And then what we're going to do is so our starting point is actually here. I was about to do it right here, but so for I guess node in degrees, if in degrees node is equal to 1, then we're going to q dot append node. So basically, like I mentioned before, we're going to add all vertices or nodes with 1 in degree, because that means that it is a leaf node, right? And then, and what we're going to do is erase all leaf nodes until we get down to essentially the center of the graph, which will give us the answer. Oh, actually, so this is a better visualization, right? So using n equals 4, this example here, let me make sure that my mouse is being recorded. It is. Okay, very nice. So basically, if you see here, we have 0, 1, 2, 3. And then if we were to get rid of all the leaf nodes, we get to 1, which is our solution, right? And then this shows the proper height that we want. And then so if we were to look at this one with 2 as the root, when we get rid of all the leaf nodes again, it's the same graph as this, right? Just rotated. But if we get rid of all the leaf nodes, then that's what we're going to get left with. So if we were to build this separately, you would be able to see that if we kept getting rid of the leaf nodes, that 3 and 4 would end up having the same heights. I mean, it's sort of shown here too, right? So if you get rid of all the leaf nodes here, so you'd get rid of 5, 0, 1, 2, so you're left with 4 and 3. And so you can just return that because this is the same thing as our edge case. So with 4 and 3, you can just return that. So we know that's our answer. But here also at 3, if we were to get rid of all of these, it would be 0, 1, 2, 5. Same thing here. And then you're back to 3 and 4. Right? So this is why we're doing this for a node in degrees, and then we're getting all the leaf nodes. And so we're going to, so actually, let me get rid of that. Let's do this here. So we're going to have a visited is equal to a set of our queue. So the reason why we're doing this visited is equal to set, because while we haven't visited all nodes, so while length of visited is less than n, that's going to be our condition to show that we've gone through all of the nodes, right? And then so we're going to have a length is equal to the length of q, and then for underscore in range of length. So basically here we need to parse through all of the leaf nodes and erase them. Add the new leaf nodes that we get to the queue. So for underscore in range of length, we're going to do popped is equal to q dot pop left, and then we're going to do for node in out degrees popped. We're going to do in degrees node minus equals 1 if in degrees node is equal to 0. Oh no, is equal to 1, sorry. The reason why it's 1 is because we want leaf nodes. It's actually impossible for it to be 0 because it has to be attached to something, I believe. So for us to erase it, right? Because otherwise, if it's 0, then it's not even a node on the tree anymore. So it has to be if node is equal to 1, actually. So we'll do q dot append node, and we're also going to do visited dot add node. And then so basically we're going to keep going through this, and then eventually the length of visited should equal n. Otherwise this edges is not a complete tree for us. So I mean, I guess that can be a different problem. And so, but assuming that they give us all correct inputs, we should have length of visited is equal to n, and we will have something in the queue because our condition is not while queue, right? Our condition is now while the length of visited is less than n. So that means once we have visited all the nodes, we should have something in our queue. So we can just return our queue. Return our queue. And and that should give us the last node or nodes of our tree, of our minimum height trees, right? So if we were to run this, this should pass the 2 test cases that are provided. So now let's run this as well. And boom, we have okay runtime. I guess we do use a lot of space since we do store both out degrees and in degrees. It might actually be possible. No, actually not. I think it could be possible that we can just go without visited instead. To maybe save some space. But at the same time, think it could be. It's still O of n space though, regardless, because we're just having O of n items in degrees, O of n items in out degrees, and then O of n items in visited. So it's all O of n, but I think in terms of real, like I think this is megabits or megabits, I'm pretty sure. In real, like actual memory, we could probably save a bit more, but it does work. So, but yeah, so that will be the question for today. Thanks everyone for watching, and if you have any questions, comments, or concerns, feel free to leave them in the comments below. Yeah, okay, see ya.